We'll first introduce our discussion by talking about population growing at a constant number versus a constant percentage. Suppose we have a population that's 50,000 in January 2002. Let's compare the trend of the city's populations if it was first increased by 1,000 people per year, and second if it were increased by 10% per year. Suppose the populations increased by a constant number, 1,000 per year. That means in 2003, it added 1,000 people, so it started at 50,000, added 1,000, and ended up at 51,000. Similarly, in 04, it added another 1,000, and ended up at 52,000. 05, it added another 1,000, ended up at 53,000. And in 06, it added another 1,000, ended up at 54,000. The graph increases steadily up by 1,000 each year. Now we know this is a linear function because we know there's a constant growth rate. The difference between each year, each unit increment of our input is 1,000 increase. So we know that our function is p of t is the initial value plus the growth rate times t. So I start at an initial population of 50,000 plus 1,000 for each additional year after that. If I compare this with a constant percentage, I'm going by 10% a year. I start with 50,000, but I grow 10% of the 50,000, which is 5,000, and end up at 55,000. My second year I start at 55,000, but my 10% growth just doesn't go to the 50,000 originally. It goes to the 50,000 plus the new 5,000, so it goes to the 55,000. So at the end of the second year, I'm at 60,500. Similarly, at the end of the third year, I'm at 66,550, and at the end of the fourth year, I'm at 73,205. This is not a linear growth model. While the data points may appear linear at first, if you look at the difference here, the delta between these, this is not a consistent growth rate. This is 5,500 here, then it's 5,550 here, and so on. This is actually an exponential growth. And we can write exponential growth as the initial value times what's called a compounding factor raised to the t power. Now your compounding factor is defined to be 1 plus your rate. You grew at 10% a year, which is 0.10, so 1 plus 0.10 is 1.1. So 50,000 times 1.1 to the t power. Let's compare and contrast these two growth rates. A linear growth adds a fixed amount to the previous y for each unit increase in x. In this case, it was 1,000 each y for each year in x. An exponential growth multiplies the fixed amount to the previous y for each unit increase in x. In other words, we multiply the 1.1. My 1.1 is multiplied to y for each increase of 1 in x. For the exponential, the 1,000 is added to y for each increase of 1 in x for linear. Please understand, because of the multiplication, exponential growth will always outpace linear growth if given enough time. Even though linear may start higher, in this case they start at the same place, the exponential growth will eventually outpace it if given enough time. Definition of an exponential function. We define exponential functions to be f of x equals c times a to the x. Your c is some constant. We assume c is greater than 0. And we assume a is greater than 0 as well. A is your base. Your a, we do not let a be equal to 1, because if a is 1, 1 to any power is 1, and this becomes a very boring function. The reason it's called an exponential function is because x is in the exponent. Now notice if a is greater than 1, this is what's called exponential growth. It's getting bigger and bigger. And if a is less than 1, this is called exponential decay. It's actually something that's shrinking. C is actually the initial value, or the y-intercept of your graph. Now please don't confuse polynomial equations and exponential ones. This is f of x equals x squared. This is f of x equals 2x. Notice the base here is x and the exponent's 2. Notice the base here is 2 and the exponent's x. Polynomial functions have bases which are variables. Exponential functions have your variables and the exponents. Notice the distinct difference between these two graphs. Alright, let's see if we can identify linear functions from exponential functions based on the table of their datas. Here's my data, the t and the p of t. We calculated this originally. The delta t in this case is 1 each time. From 1 to 0 is 1 year, from 2 to 1 is 1 year. The delta p of t is 1,000. 51,000 minus 50, 52,000 minus 51,000. So the delta p of t over the delta t is 1,000. It's constant each time. This is an example of a linear function. In fact, if you sat there and got all your data points, your linear functions would have slopes that are constant regardless of the pair of points that you picked. Now, exponential functions have constant ratios of consecutive y values. My ratios are one y value to the prior y value. The only caveat here is that the unit value in the t or the x has to be the same as well. In this case, my unit value increases 1 for each of these. Over here, notice the ratio, 55,000 over 50,000 is 1.1. 60,500 divided by 55,000 is 1.1. This is how we can identify linear functions from exponential functions when we're simply given the data tables. Is the following function linear or exponential? If we look at it, the unit values for x all increase by 1, so all we really need to do is focus on the y values. Notice the y values all decrease by 5. 4 to negative 1 is a decrease of 5. Negative 1 to negative 6 is a decrease of 5. So this is actually the difference in y. This is actually our slope too. Since this is increasing by 1, that's my delta x. My delta y is negative 5. Negative 5 over 1 is negative 5. So that's y equals mx plus b. This is negative 5 for m. And we know by definition your b is your y-intercept, or where x equals 0. And here's where x equals 0 at 0, negative 11. So this function is y equals negative 5x minus 11. Now, if I look at my another example, is this linear exponential? This, again, your delta x is 1 all the way up. Your y, this grows by 4, then it grows by 12, then it grows by 20, so this is not linear. But if we take a ratio of it, 8 over 4 is 2, 16 over 8 is 2, 32 over 16 is 2. This is growing by a ratio or a factor of 2 each time. This 2 is the factor that goes in here for your a, your compounding factor. Remember we said c was your initial value. In other words, your initial value is where x is 0. So 0 comma 32. So 32 is c, a is 2. So y is 32 times 2 to the x power. Let's compare exponential growth versus exponential decay. Remember we said the only real difference is that the a has to be greater than 1 for growth, and the a has to be between 0 and 1 for decay. Now I'm going to choose 2 over here on the left-hand side for growth. I'm going to choose 1/2 over here on the right-hand side for decay. I also want to point something out real quick, okay? 1/2 can be written as 2 to the negative 1 power. So if I look at this function, I can write 4 times 1/2 to the x power as 4 times 2 to the negative x. So when you see something like this, these two are equivalent. So if I have a number between 0 and 1 and a positive x up here, it's decay. If I have a number greater than 1 with a negative x, it's also decay. Notice the domain of each is negative infinity to infinity because I can plug in any number I want. Notice the range is 0 to infinity. I don't include 0 because there is a horizontal asymptote at y equals 0 for both of these. And notice the y-intercept is at 0, 4 for each graph as well. The biggest difference is that growth increases left to right. Notice this slope of this line, of this graph, increases steadily left to right. Notice the slope of this graph decreases steadily left to right. So the function decreases from negative infinity to infinity. Why would we use exponential decay? Well, exponential decay is used a lot. The most common example is in radioactive dating. The time it takes for elements of an atom to decay into different elements is called the half-life of an element undergoing radioactive decay. The half-life of carbon-14 is 5,700 years. For example, if c grams of carbon-14 are present at time t equals 0 years, then after 5,700 years there will be c over 2, or approximately half the amount of grams of the carbon-14 present. Now we come up with a formula we can work out for half-lives, If a radioactive sample containing C units has a half-life of K years, then the amount remaining after X years is given by A of X equals C times 1/2 X over K. And again, we're talking about years here. We can change it if we're not dealing with years. Let's look at an example. Rituxan is used in chemotherapy and has a half-life of 76 hours for its initial dose. What percentage of Rituxan is left in this system after 10 days? Well, I'm going to use this formula, A of X equals C times 1/2 X over K. I don't know what C is because I'm not really told how much the initial dose was. But I am told that the length is 10 days, and my half-life was given in hours, so I'm going to change days to hours. So 10 days is equivalent to 240 hours. The half-life is 76 hours. So 1/2 to the 240 over 76 power is approximately 0.112. So if C grams is initially administered, then after 10 days, 0.112 times C remains, so 11.2% remains after 10 days. Let's talk about exponential growth as it applies to compound interest. Suppose we have $1,000 deposited into an account which pays 8% interest compounded annually. What's the balance in the account after 40 years if nothing else is deposited? This is a simple exponential growth model. P of t equals C times A to the t power. C is the initial value, so we have $10,000 in it. Your compounding factor is 1.08. Remember I said it was 1 plus the rate. So 1 plus 0.08 is 1.08 to the 40th power. So if I don't do anything after 40 years, I'm going to have $217,245.21 remaining in the account. Now, we don't often compound just annually. That is occasionally what happens. We have annual, which is 1 time per year, semi-annual, which is 2 times per year, quarterly 4 times per year, monthly 12 times per year, and daily 365 times per year. The general formula for compounding interest is A is the amount in the account equals P the principal times 1 plus R is your rate written as a decimal divided by N, which is the number of times per year you're compounding, to the NT power. N again is the number of times per year you're compounding, T is the number of years. So suppose $50,000 is deposited into the account, which pays 12% interest compounded monthly. What is the balance in the account after 30 years if nothing else is deposited? A equals P times 1 plus R over N to the NT. P is 50,000. 1 plus 0.12 divided by 12 to the 12 times 30 power. And this gives us $1,797,482.07. The biggest factors in here are time, and the interest rate is fairly significant at 12% per year. There's something called the natural exponential function, which is f of x equals e to the x. E is a base. E is kind of like pi. It never repeats itself. E is approximately 2.71828. I don't think the last 1828 is correct. I'm going to get rid of those. I apologize. I think I typed those in twice. You do not need to memorize E, okay? Because E is in your calculator. Okay, it's right above the LN button. So, if a principal of P dollars is deposited in an account paying an annual rate of interest R compounded continuously, this is the big key here. It's compounded continuously. If you see continuously, you should automatically think this formula. A equals P e to the RT. I call it my PERT formula because that's basically what it spells. Suppose $30,000 is deposited into an account which pays 10% interest compounded continuously. What is the balance in the account after 30 years if nothing else is deposited? A equals P e to the RT. P is 30,000. R is 0.10. T is 30. So at the end of 30 years, you will have $602,566.11.